Assalamualaikum and hello to everyone. In this video lesson, we will continue with chapter 4 of our syllabus. In this video lesson, we will continue with the fourth subtopic as highlighted on the left. For this video lesson, we will look at the reheat Rankine cycle under actual conditions. The objective for the subtopic is on the right of the screen. In the previous video lesson, we have seen on how to analyze the reheat Rankine cycle under ideal conditions. However, for actual cases, due to irreversibilities that happens in pumps and turbines, it is necessary to consider the isentropic efficiency of these devices. An example for a TS diagram under actual conditions is shown in the figure given. For isentropic efficiency, we have covered the topic in chapter 3 and also in the previous cycle. Therefore, these equations should not be new to all of you. Just a quick reminder that for actual conditions, we must use the subscript A, and for ideal conditions, we will use the subscript S. And it is also important to know which component we should consider its isentropic efficiency. Now, it is important that students identify which states are involved for each of the isentropic efficiency. Make sure to read the question to identify which components that must be taken into consideration its isentropic efficiency. For components which does not have the isentropic efficiency, we will treat them as an ideal or isentropic process. The following equations on the left are the working parameters for the reheat Rankine cycle based on actual conditions. Please be careful when writing the equations. Make sure to include all required states in the equation. On the right are the performance parameters for the reheat Rankine cycle. Basically, these performance parameters are the same as in the previous cycles. Now, let's look at an example for the reheat Rankine cycle under actual conditions. You can pause the video to read and understand the question properly. Now, for this question, there are isentropic efficiencies at the pump and both of the turbines. Make sure to identify the value for the isentropic efficiencies for the respective components. For step 1, please try to draw and label the schematic diagram by referring to the previous slides. For step 2, the first item is to determine the exit temperature at the low pressure turbine. Since there is an isentropic efficiency at the low pressure turbine, the exit temperature here is the actual exit temperature at state 6. For the second item, to find for thermal efficiency, we will use the thermal efficiency equation as seen in the previous slide. For the third item, to find for mass flow rate using the net work output given, which is 80 megawatts, we can solve for the mass flow rate using the following equation. For step 3, determine the required properties at each of the state. Now, this step has been done numerous times, and by now students should be well versed when finding the properties at each state. At state 1, based on the given information, read for specific enthalpy and specific volume. At state 2, since there is an isentropic efficiency here at the pump, we must first solve for the ideal process. Use the required equations to find for the ideal specific enthalpy here at state 2. To find for actual specific enthalpy at state 2, we will use the isentropic efficiency equation here at the pump. Solving the equation, we can calculate for the actual specific enthalpy at state 2. At state 3, based on the given information, read for specific enthalpy and specific entropy, but remember to check for the phase first. At state 4, since there is an isentropic efficiency Here at the high pressure turbine, we must solve for the ideal process first, use the required properties to find for the ideal specific enthalpy at state 4. Now, to find for the actual specific enthalpy at state 4, we will use the isentropic efficiency equation at the high pressure turbine. Solving the equation, we can solve for the actual specific enthalpy at state 4. At state 5, based on the given information, read for the specific enthalpy and specific entropy here at state 5. Now at state 6, since there is an isentropic efficiency here at the low pressure turbine, we must solve for the ideal process first, and using the required properties, we can solve for the ideal specific enthalpy at state 6. Now, as you can see, the phase is a mixture, so we must use the equation for mixture to find the ideal specific enthalpy. Now, to find for the actual specific enthalpy at state 6, we will use the isentropic efficiency equation at the low pressure turbine. Solving the equation, we can calculate for the actual specific enthalpy at state 6. And also, we can now solve for the first item, which was asked in the question, which is to find the actual exit temperature at state 6. Using table A5, based on the known properties, we can see that the actual phase for state 6 is in the superheated form. Therefore, by using table A6, based on the known properties, we can interpolate for the actual exit temperature at the low pressure turbine. For step 4, substitute and solve for the remaining items. To solve for the thermal efficiency, make sure to calculate all the required parameters individually, and only then calculate the thermal efficiency for the cycle. To solve for mass flow rate, simply substitute the required values into the equation and solve for the mass flow rate. Now we have come to the end of this video lesson and also the end of chapter 4. For questions, please refer to the tutorial that has been provided. Thank you for your attention and have a good day. If there are any questions regarding any of the examples, please ask me for more information. Thank you.